Hi guys, and welcome to lecture 4 of Python programming with me, Mace. So in the last video we went over arithmetic and assignment operators. However, there are actually two other operators that we didn't talk about, which are bitwise and logic operators. So in the next few lectures, we're actually going to go over bitwise and logic, and you may be asking, why do we need more than one lecture to go over bitwise and logic operators? That's because we're going to be learning about binary. So how does binary work? Everybody knows that binary is 0 and 1. It's just a basic concept that everybody's taught, 0 or 1. And as you know, or as you should know, that everything in the computer is either a 0 or a 1. Everything the computer calculates is 0 or 1. Although you may be thinking, why 0 and 1? Why isn't it, our number system? Or why doesn't the computer store it as letters? And it all comes down to memory, because 0 and 1, they take up not much space at all. They are very condensed. And see, the reason is, when we write down a number, for example, in binary, so we'll get to actually converting numbers to binary manually later in the video. But when you write down a number, such as 10, which is 10, 10, that's actually 10. Is it 10? Yes, it's 10. So when we actually get down to writing numbers like these, we could just write down the number and the computer would understand it as 72. However, that takes up a lot of memory. So what we use is bits. One of these binary digits is 1 bit. And when you have 8 of these digits, 3, 4, 5, 6, 7, 8. We'll just replace that with a 1 because I feel like it. When you have 8 of these bits, you have 1 byte. So you may have heard the term 64-bit computer. That means the computer can process 64 of these 1010s at a time. So a CPU can calculate that at a time. So without further ado, let's get started with conversions from decimal to binary. Okay. So decimal is our number system. Everybody knows it, and it's quite a large number system. So our number system decimal, which we'll make into the shorter form dec, is base 10, which means we have 10 digits, 0 to 9. Everything in base 10 is either 0, 1, 2, 3, 4, 5, 6, 7, 8, or 9. Every number that we know is made up of those 10 digits. However, binary, on the other hand, is base 2, which means it's 0 to 1. There are only 2 digits, 0 and 1. And that extends on to the concept of taking up not as much space. Anyway, so how do we convert from base 10? So let's take a number 31, for example. 31 to binary. First, we need to actually understand that binary is base 2, like I said before, base 2. So we need to convert from base 10 to base 2. How do we do that? So first, let's write down the powers of 2. So 2 to the power of 0 equals 1. 2 to the power of 1 equals 2. 2 to the power of 2 equals 4. And you should know this from school. 2 to the power of 3 equals, you guessed it, 8. 2 to the power of 4 equals 16. And we're going to keep on going until we get just over 32. 32. That looks like 25. Yeah. Okay, so now that we're just over 31, we got to look at the power that is 31 or below, like 31 or less. So we can find that it's 16. 32 is above 31, so we go to 16, which is 31 or below. Well, that means we do 31. Our next step is to do 31. Whoops. So now that we know it's 16, we do 16 plus 15 because that's a leftover. So we've condensed 31 to 16 plus 15. However, that is not finished because 15 is not in this list. So we got to go 16 plus 15 to 16 plus 15. So what is less than 15? 8, right? So do 16 plus 8 plus 15 minus 8 is 7. So 16 plus 8 plus 7. However, 7 is still not on this list, and we repeat that process for 7 again, which means we get 4. So it's 16 plus 8 plus 4 plus 3, because 4 plus 3 is 7. So now you have 16 plus 8 plus 4 plus 3, but 3 is not on this list either, so we have to do it yet again. So now we have 16 plus 8 plus 4 plus 2, because it's on its list, and plus 1, because 2 plus 1 is 3. And is 1 on the list? Yes, it is. So now we finished that. Now, quite coincidentally, this is in order, if you haven't realized, 1, 2, 4, 8, 16. In fact, 31 is the only number that is in order like that. I mean, there are numbers that go 1, 2, 4, 8, 16, 32, and so on. But, I just chose 31 randomly, and it's 1, 2, 4, 8, 16. So, so just keep in mind that it's not always going to be in order. Sometimes it's like 1 plus 4 plus 16, or something like that. So it's not always going to be like that ranged up. Okay, so what you may be thinking right now, how does this relate to binary, zeros and ones? So now we actually have to go 31, 2, so this is going to be our direct conversion. Because it's powers of 2s, we're going to go 1s, 2s, 3s. Oh, whoops, not 3s. Sorry. 4s. Because we're doubling, because it's powers of 2. 16s. Okay, and now we go, how many 1s are there? We have 1, 1. How many 2s are there? We have 1, 2. How many 4s are there? We have 1, 4. How many 8s are there? We have 1, 8. How many 16s are there? We have 1, 16. So in binary form, 1, 2, 3, 4, 5. It is 5 1s. However, notice that sometimes it could be 16 plus 8 plus 2 plus 1, which means because there's no 4s, we would have put 0 if we had something like that. So it's either 1 or 0. Now, as I said earlier in this video, we actually want to condense this into 8-bit form, which means we do 0, 0, 0, 1, 1, 1, 1. Oh, it's 5 1s. So that in 8-bit form right there, in 8-bit form is our binary of 31. Okay. So now that we know how to convert from base 10 to base 2, decimal to binary, let's do binary back to decimal. And that doesn't really require that much explaining, because we just got to start the other way. So let's do 1s, 2s, 4s, 8s, 16s, 32s, and 64s. We'll make it a 1, 2, 3, 4, 5, 6, 7-bit number. That's not perfect. We'll do 128s. Now we have an 8-bit number. So now we go, let's just make a random one. 0, 1, 0, 0, 1, 1, 1, 0. Okay. So first we got to see, are there any 1s? No. Are there any 2s? Yes, there's 1, 2, which means we do 2 plus, no 4s, no 8s. Oh, let's just make that 16. There's 1 16, so we do 2 plus 16, plus 132, as you can see there, and plus 164. And there's no 128. So now we add that up, which is 18, quick maths, 18 plus 32 plus 64, which is 50 plus 64, which is 114. So 0111010 is 114. And notice that we calculated all of that manually without a computer. So our next conversion will be text to binary. So when we say text, we mean any character, really. So we have characters like A, B, C, D, E, F, G, anything on your keyboard. So we have A, capital, lowercase a, B, capital, lowercase b. Oh, whoops, that's not lowercase. And so on. Okay? So, how do we actually convert from text to binary? Now, the funny thing is, with text from binary, you can't actually manually do it. You need the assistance, unless you've memorized this, you need the assistance of the ASCII table. So, let's search this up on Google. ASCII table. And it's loading, wait for it. This is the ASCII table, ascii.com. ASCIItable.com. So the ASCII table is a list of every character that you have, plus some extended characters, which you won't be using that much at all. And so what you're going to be most using are these right here. These three columns right here. So capital A So what this ASCII table does actually is converts a character into its decimal form. So capital A here is represented by 65, and capital lowercase a is 97. So unless you actually memorize this table, you will have to refer to this chart. However, you don't actually have to memorize it. As long as you remember that capital A is 65, you can just count down, and then as long as you remember 97 is lowercase a, you already have the codes for all the letters in the alphabet, lowercase and uppercase. Okay, so with that in mind, let's go back to our sketchpad and let's convert. So what letter do we want to convert? We want to convert, let's do a word. So let's convert the word cool. Yes, we'll do the word cool. Actually, no, we'll do the word bow. Bow. Okay. So what is B in the ASCII? So if you know it, it's A capital B. Capital A is 65, so B must be 66. O, we'll have to refer back to the chart for that. And if we look at O, which is lowercase, we have 111. So we have two 111s, and our L is 108. So we have 111. Oh, wait, and our... Oh, whoops, we're not doing cool, are we? And our W is, let's have a look, is 119. So now that we know the ASCII codes for the bow, we just have to convert these into binary. So let's start with 66. So 66 in binary is, if we remember by memory, we know the power is 64. So 66 equals 64 plus 2, and 2 is a power, which means we don't need to do anything. So then we have 0. So we have 1s, 2s, 4s, 8s, 16s, 32s, 64s, and we have 0 1s, 1 2, and 0 0 0 0 1. So that is your binary for B. Okay, so now let's go to 111. 111 is yet again 64. However, it's actually 64 plus 36, 46, 47, plus 47. 47, however, doesn't work, so we do plus 32 plus 15. Plus 32 plus 15. 15 still doesn't work, so we do 8 plus 7. And 7 doesn't work again, so we do 8 plus 4 plus 3, which doesn't work. We do plus 2 plus 1. So that's actually the same as 31 from earlier, but we add the 64. So now we have 64 plus 32 plus 8 plus 4 plus 2 plus 1. Okay. Oh, but we don't have a 16 this time, which you may have noticed. Okay, so now we just go. There is 1 1, 1 2, 1 4, 1 8, 0 16s, 132, and 164, which means in ASCII, O is 110, 1111. Our last one is 119. So now we'll just go to 119, which I can't explain. I can, but just to be quicker, I won't. So we know that it's 110. So 119 is actually 111, 0111. So now we have the three ASCII values: 10000010, 1100010, 11011111, 111011. Now we can actually do bow. So B is 100010, and O is 11110111. And oh wait, we'll just add zeros in front of them to convert them into 8-bit form. Actually, we don't even need to do that because ASCII is in fact 7-bit. So now we have our next one, which is 110111. So that right there is bow in binary, though. Now you may be wondering right now, how do we then tell the difference between 66, 111, and 119? After all, this actually just reads 66, 111, and 119, doesn't it? So that we can't actually do it. However, the computer, when we do arithmetic operations, when we do any operations really, with these binaries, the computer will automatically recognize whether it's a string or if it's a number. For example, you can't actually do A times B if A is, bow and B is bow as well. You can't do bow times bow. It doesn't work. So the computer automatically recognizes, no, it is not 66,111,119 times 66,111,119. It is actually, it isn't bow times bow. It's 66 times 66,111,119 times 66,111,119. So that is just converting from binary to text. Decimal to, converting text to binary. Okay, so now we go on to our next conversion. Converting hexadecimal. So what is hexadecimal? Hexadecimal is another version of binary. Not a version of binary. It's another language used by computers. Although it's more memory intensive and not used as much, it is still important to know. So unlike binary, which is base 2, hexadecimal is actually base 16, which is even more than decimal, which sits in the middle at base 10. So how do we actually transfer between decimal and hexadecimal? So it's actually quite simple. It is literally the same as doing this, except you're literally doing it the other way. Okay, so let's have a look at this. Say we have the decimal number 70. Let me think. Say we have the decimal number 2000, okay? And we want to convert it to hexadecimal, okay? Okay, so first of all, we do the same thing we did with binary. We do 16 powers. However, with binary, we did 2 to the power. Here we're doing 16 to the power because it's base 16. 16 to 0 equals 1, 16 to 1 equals 16, 16 to 2 equals 256, and 16 to 3, equals, 1496. Okay, let's go. Now we do the exact same thing we did before. What is lower than 2000? So what we can see here that is lower than 2000 is indeed 256. So, just out of memory, I know that 7 256s. Let's check this. 256 times 7 is 42. 5 times 7 is 35, 39. 2 times 7 is 14, 15, 17. 1792. Which indeed is how many 256 is going to 2000. So 2000 actually equals 256 times 7. So I could just do the same as I did before. 256 plus 256 plus 256. But it's just better to do 256 times 7. However, we still have a remainder of 2000 minus 1792. So if we do 2000 minus 1792, we'll find out that it's indeed 208. So now we do 2000 equals 256 times 7 plus 208, and 208 is actually 16, so we got to do plus 16 times, and how many 16s going to 208? Well, we'll have to calculate that ourselves, so let's go. 208 divided by 16, we can do short division for that. One remainder, 4. How many 16s going to 48? That is 3. So we have 13 of them. So now we just erase all of this just to give a small room. And now we can represent 2000 in hexadecimal form. So now that we know it's 256, so I've just cleared the rest of the sketchpad to make it easier to understand. So now that we know that 2000 is 256 times 7 plus 16 times 13, we can represent this in hexadecimal form. So it is important to do the exact same thing we did with binary. So let's just write down the powers again. So we have our 1, we have our 16, we have our 256, and we have our 4096. So how many 1s? We have our 1s, our 16s, our 256s, and our 4096s. So how many 1s do we have? Now it is important to keep the 1 in place, okay? Just because we don't have any 1s doesn't mean we can ignore it, okay? So we have 0 1s. How many 16s do we have? We have 13 16s. How many 256s do we have? 7. And how many 4096s? 0. So we can just get rid of that to make it easier to understand. So 7, 13, 0. And anybody that actually watched that knows hexadecimal, you may have realized that 13 isn't actually in hexadecimal form. So let's talk about that now. What is hexadecimal? Okay, so hexadecimal is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, F. It is the same as our base 10 system, but it replaces the 10, 11, 12, 13, 14, and 15 with letters. So as you can see here, 13 is in fact D, so it's actually 7DO. And that is the in fact answer. In fact, if we check it right here, we can see 2000 in hex is 7D0. And that wraps it up. Okay, so and that is converting to from hexadecimal, from decimal to hexadecimal. And we have one more conversion we're going to do today, which is, let's get rid of all of this. Convert. I will just get rid of it. It is actually hex to binary. Binary to hexadecimal, which is more of a convenient way of doing it. Binary to hexadecimal. So how does binary to hex... Oh, whoops, that X isn't really good. That one isn't good either. So how do we do this? Now, what the funny thing about doing this is binary is base 2, right? And hex is base 16. I realize something? Yeah, I do. 16 is a power of 2, which makes converting really fun and really easy. So let's go. Okay, so what do we want to convert from binary? Let's convert 12 into hexadecimal. Actually, no, let's not do 12. Let's do 2000, which let's calculate 2000 in binary. Okay, so let's go 2000 in binary. Actually, no, we'll just do any random binary, really. So we can go 0, 1, 1, 0, 0, 1, 1, 0, 0, 1, 2, 3, 4, 5, 6, 7, 8. Okay, that's 8 right there. And it's quite important to use your 1s, 2s, 4s, 8s here. It's just like a guide. 16s, 32s, 64s, 128s. And now we can convert to hexadecimal. As I said before, we have powers of 16. So if we look here, if we just look at this one section, forget about these 4 here, just the 1s, 2s, 4s, and 8s, you might realize that for the 1s, you can have a total of 16 1s. Let's count it up. 1 plus 2 is 3, plus 4 is 7, plus 8 is 15. So that means you can have exactly 15 1s, which makes converting in the base really easy. Same here, we can have, instead of 1s, we use 16s. We can have exactly 15 16s, which I won't calculate here, but it just happens to be so. So, how many 1s do we have here? Let's see. We have 6 1s. Okay, we have we have 4, 5, 6 1s. And here we have 3 16s. Okay? Which means in hexadecimal form, the binary of 0011 is indeed 36. So let's check that out. So 0011. Okay, so we go back here. 00. Let's just check what it was again. 0011 0110 to hexadecimal. And let's just go here. Okay, so our binary value is 0011 0110. Let's convert. 36. And what did we get here? We had 36. So that was our last conversion, binary to hexadecimal. And even though the one you are going to use most is decimal to binary and binary to decimal, all of these conversions are good to know and good to understand. Anyway, if you have any trouble, just write something in the comments section and see you in the next lecture.